I'm here at the Mile High Design Center in Fort Collins, and we're going to be talking about AMD's new R-Series processor. Could you tell us about the architecture?
Sure. This is a brand new product for us, and it's going to contain the pile driver core. This is a second generation of the bulldozer microarchitecture. We've made significant advances in power efficiency as well as performance with this core.
Well, great. Could you tell us a little bit about some of the characteristics? How many cores does this have, and where are we going to find this in terms of embedded applications?
Sure. So we're talking about the embedded R-Series product here. This contains up to 2 core pairs, 4 total cores on the chip. One of the things that's unique about our microarchitecture is rather than using hyper-threading, we actually have independent resources available for the cores to use, as well as shared resources which enable us to get better throughput and power efficiency.
So what are some of the shared resources?
Well, hey, we've got this great picture behind us. We'll take a little bit of a look at it here. But this kind of shows one of the core pairs, a second one over here. Some of the shared resources that we have is we have a shared 2 megabyte level 2 cache. And we also have a shared high-performance floating point unit. And lastly, we share the instruction fetch and decode portions. This allows, again, the sharing allows power efficiency and better resource utilization. And the separate resources, which are completely independent integer cores, allow for better throughput without having to worry about competing for the same resources there.
One of the things you can do is actually balance the power between both the processor and the GPU, depending upon what your needs are.
Yeah, thanks, Bill. That's one of the really important features with this microarchitecture. Power efficiency is crucial with today's processors, and so is performance. And so when the application is using something that's more graphical intensive, we can shift power over to the GPU, enabling that to operate at higher performance and basically steal power from the CPUs, enabling them to not burn power, again, with more efficiency and greater performance.
What does that do to the power dissipation of the chip?
And actually, that's the interesting part about it, is the overall power dissipation and thermal envelope are managed within a separate processor on the die. There's a small processor that's continually understanding how much power and energy each portion of the chip is demanding and using. And unlike past power management, we actually balance within a thermal envelope. And so the core is aware, the chip is aware that it's been in a low power state for a while and the chip is relatively cool. So it knows that it can go to maximum boost, giving you great performance for applications that go in and out of a high performance state. And we've actually done modeling of the thermal energy actually moving from either 1 core, 2 cores active, GPU active, and actually it's really interesting to watch how the overall power is managed between all the different components in the system.
Now, what does this do to operating systems? Do they need to be tailored to this? Is it transparent?
Yeah, this is all completely transparent to the operating system. It's all managed on chip. Yeah.
Well, excellent. In terms of overall performance, how do you compare this to some of the multi-chip solutions? Obviously, this is going to be much more power efficient overall.
Than a multi-chip solution, absolutely, right? Because all the signals are contained on one die. The graphics is able to use the same memory as the CPU. All of that sharing results in not only a much smaller form factor, but a lot greater power efficiency.
Well, great. I'm looking forward to seeing one of these in one of my systems.
Oh, thank you, Bill.